Hi, I'm Michael Tsirkin from Red Hat. I'm the chair of the Virtio Technical Committee, and part of my job, I maintain the Virtio family of para-virtualized interfaces. This talk is going to be about future directions for Virtio. So it's not going to be a status update. I chose to focus on where we are heading next, this year and the next one. So the first thing first thing I'm going to mention is that Virtio 1.0 is heading towards becoming an OASIS standard. The current status is committee specification. This means that it went through public review without lots of issues. To become an OASIS standard, the requirement is to have 3 statements of use, and I'm happy to report that at all 3 levels in the stack, we have at least 3 implementations. You can use Linux kernel drivers and Windows kernel drivers within the guest, and you can also use DPDK user space drivers within the guest. Device ROMs supporting Virtio 1.0 exist and are used by BIOS, OVMF, and OpenFirmware. And on the host side, QEMU has full support for Virtio 1.0. Additionally, DPDK supports it through the vhost library, and there are vhostnet and SCSI drivers in the Linux. So we are all set with that. And we are starting to plan the next version. The next version of the Virtio specification, which will be revision 1.1. And there I expect us, first of all, to move forward with standardization of new interfaces, implementations for which are already upstream. So this includes relatively new devices, such as Virtio Input and Virtio GPU, Virtio Socket device, and maybe some older devices like the 9P file system, if we can find someone who can write it up. Volunteers are always welcome. So we're also going to standardize some recent upstream features, such as virtual IOMMU support, which is required, for example, for safe usage of guest user space drivers with Virtio devices. And I'm going to discuss this a bit later in this talk. That's not all. I expect a slew of new devices. So there's Virtio crypto device, which offloads crypto capabilities to the host. The persistent storage device, a signaling device, which can send interrupts to CPUs. That's kind of interesting, and I'm going to discuss this a bit later. Maybe a shared memory device, and likely some more. Existing devices will gain new features. I'm rather confident that Balloon device will gain ability to report page usage hints to the host. And this is helpful to improve the placement of guest memory on the hypervisor. We might see new transport integrated in the standard. vhost PCI is very interesting. It allows one virtual machine to access the memory of another using a Virtio device. And finally, we will see a bunch of changes that enable new performance optimizations. And some of these I'm going to discuss next. So here's starting with the charts. So how much overhead does passing messages between host and guest CPUs using Virtio incur? Right? This chart shows per request processing time, depending on the batch size. And by batch size here, I simply mean the maximum number of outstanding requests in the queue. So you can see that increasing batching size decreases the processing time per request. Why would that be? This is not due to signaling, because this test actually used polling exclusively on both the host, the consumer, and guest, the producer of requests. So there are two main reasons for batch size. being helpful. The first has to do with pipelining. So if we limit ourselves to a single outstanding buffer, then CPUs running both the host and the guest spend a bunch of time idly waiting for a new request to arrive in case of the host, or for the previous request to be processed so a new one can be added in case of the guest. And we have to count this time, right, as part of the processing time for the request. So if we just allow guests to submit multiple buffers synchronously, suddenly processing time per buffer decreases because the buffers are now processed in previously idle time. Right? So that's one reason why batching is helpful. But there is another one, and it has to do with CPU caching. So if two CPUs are communicating using shared memory, one of these would typically modify a location in memory, and then another one has to read it, and like it proceeds in repeatedly. And when this happens, the caches of the two CPU have to be synchronized. This could involve cache invalidations. This could involve what kind of synchronizations, cache misses. And the number of these misses directly impacts communication latency. So I'm going to show that as you increase batching, the number of these misses decreases, right? That's why performance goes up. Let's take a look at Virtio 1.0. This is roughly how a Virtio queue, virtual queue looks. You have 5 data structures linked together. You have to access all of these in order to pass a message to host and get notification that message has been processed. You have the available index pointing into available ring, pointing to descriptor, and then you store the process descriptor index in the used ring and update the used index. So we have 5 parts, and as buffer moves between host and the guest, each of these parts is written and read at least once. So this means at least 5 cache misses per buffer, if no batching is allowed. Now with batching, the per buffer overhead is lower because multiple buffers fit in a single cache line. How many buffers would fit in a single cache line depends on the batch size and depends on the cache line size. So for example, if we have a batch size set to 4 and the cache line happens to be 64 byte, then each cache line holds 4 entries of each kind, right, of each of the 5 kinds. And this gives us 5 misses per 4 requests, right, 1 and 25. So that's the second reason why batching is helpful. Between the two effects, which one is the more influential? Is there some way to measure how much overhead does each of the two effects contribute? So I found one trick to do this. And we could try to answer this by running the test on a hyper-threaded system. Now, a hyper-thread is in fact a partition within a physical CPU. And hyper-threads share a cache. So the cache synchronization effects mostly go away. Most of the performance overhead when running consumer and producer on 2 hyper-threads within a single CPU will be due to the pipelining and the processing overhead, right? So unfortunately, it's not a clean experiment because hyper-threads actually share some more CPU resources, and they might conflict and slow each other down. But I think it's still interesting. It kind of gives you an upper bound on the overhead of the processing and the pipelining, and helps you, at least to some extent, exclude the cache synchronization overheads. So this is the chart. And you see that most of the time in this benchmark is spent on cache synchronization, especially without batching. So the issue is these 5 parts of the queue, right? It's most noticeable without batching when these 5 parts of the queue causes 5 cache misses on each access. Well, can't we do something faster for Virtio 1.1? So here's an idea. And there's actually a prototype that you can find as part of the tools directory in Linux kernel. So instead of using 5 data structures, we will try to pack everything into the single 16-byte descriptor that we already have anyway, right? So let's try to see how can we do this. This is color-coded, so these things that are the same color, they map from Virtio 1.0 to 1.1. So we have the address field. It's unchanged. We have the length. It also goes unchanged. Just copy it in the new descriptor format. And we have the flags. It's a couple of bits. That's mostly the descriptor. I'm going to discuss next a bit later, the next pointer. Next, we have the ID field. ID appears in the available and the used ring. Instead of putting these in separate rings, we will put it as part of the descriptor itself. And we will store the descriptors in the ring structure. So the ID has it performs 2 functions. One is it identifies the descriptor, and second, it helps us locate it in the descriptor buffer. So now that we put descriptors in a ring structure, they just go one after another. We don't need to use ID to find the descriptor, right? It's just an identifier for host and the guest, unique identifier. And this also means that we don't need the next pointer. There's a next flag in the flags field, and that's enough to tell you there is a descriptor next. Just go ahead and use it. You don't need a pointer. Okay, what's next? Right, the length field is also copied in the used ring. We do not need that. We can just write directly into the descriptor. This means that we will make the descriptor writable by the host as well. And then we can reuse the length field. Sounds good. What else is left? Right, there's the available index and the used index. So this serves 2 purposes. One is they just mark a buffer valid for host or guest to use. So a single bit in the descriptor will be enough for that. That's simple. They serve another purpose, and that is to allow passes batches of descriptor atomically between host and guest. For example, the mergeable buffer feature in the networking device uses that. So we can just label descriptors. If we have a batch, we can label the first, the middle, multiple middle descriptors, and the last. And that just needs 2 bits. We don't need full indices for this. So we get a total of 3 extra bits instead of 32 bits. So like we packed everything into one writable descriptor now. Let's take a look at how this compact layout is used. So to make buffers available to host, guest just writes them out in descriptors in the ring and then sets the valid bit to 1. And this implies that it's now OK for host to use these descriptors. Host can process them in any order. We keep this feature of Virtio 1.0. Each descriptor has an identifier field. And after processing, host will write the processed descriptor ID in the ring and then flip the valid bit to 0. And this tells the guest, OK, this entry now has been used. The guest can now reuse the entry for new buffers. So you're going to see that this is much easier to implement than Virtio 1.0. The data structure is drastically simpler. Here's just pseudocode for the host. And this one kind of assumes that host is processing entries in order. As you can see, descriptor processing involves, first of all, reading the descriptor to make sure that the valid bit is set. And once we detect that it's set, we process the descriptor. Then we clear the valid bit, and this is a write. Now, if we are lucky, the read will put the descriptor in our cache, and then the write will just do a cache access. If we are not lucky, then both might cause a cache miss or invalidation. It's all architecture dependent. So this means that on the host, we get between 1 and 2 misses to process a descriptor. Still better than 5, right? And the same thing happens on the guest. It's kind of symmetrical. So if we do the math, we get between 2 and 4 misses per buffer with no batching. And half to 1 miss when batching, up to 4 buffers. This is still better than Virtio, even in the worst case. At least in theory, but as I said, I did write a small prototype, so let's take a look at the numbers. And you see that, yeah, they look pretty well, unsurprisingly. Otherwise, I wouldn't be putting this in the presentation, right? So without batching, we managed to reduce the overhead of the caching almost by a factor of 2. Right? If we consider the caching effect, everything on top of the hyper-threaded bar, right? Then we reduce that almost by a factor of 2. And with bigger batching, it's kind of smaller, but still very noticeable. I also tested the hyper-threaded performance with this different layout to measure the pipelining and processing overhead. And as you can see, it performs more or less the same as 1.0. So better cache behavior is probably the main reason that this performs well. But just this raw performance is not the only benefit of this compact layout. It actually allows us to address other performance problems that we have had for a while. So consider a networking device. Some workloads exchange predominantly small packets, but do need to get a large packet once in a while. The way we solve it now in VirtioNet is using a feature called mergeable buffers. So the way it works is that the device writes a number called numBuffers in a field, and this value will be bigger than 1 for a large packet. Now the guest has to read this value to figure out how many buffers does the packet contain. And unfortunately, this occurs a cache miss overhead per packet. It was reported that just by simply commenting out the line that reads this value improves the throughput by about 15%. Of course, at the cost of breaking the mergeable buffers feature, so you can no longer accept large packets, so we do not want that. What we can do instead is using the new layout. Since the host now labels descriptors as first, middle, and last in a batch, we no longer need the number of buffers, right, to find out where does the packet end. Guest can simply scan the descriptors until it seals the last label in the descriptor. So I expect to observe throughput improvement once we test this with a new ring layout, but we didn't yet. That's one reason this might be a good idea. Parallel processing might become simpler with a new layout. Sometimes the work request order doesn't matter. For example, that's the case when you are processing used transmit buffers in the networking device. You just free the buffer, you reuse the memory for something else. You don't really care in which order this happens. And so each descriptor is now completed independently. So with new layout, it might be possible to partition the ring such that multiple worker threads would each process a separate cache line that will not conflict with each other, and maybe we'll get some performance out of this. I/O interrupts are expensive. And so Virtio Ring actually has 2 mechanisms for I/O interrupt mitigation. One is the event index, and one is the flags. I didn't really examine them for cache efficiency. Both seem to have advantages and disadvantages, and this really has to be done. But with 1.1 compact layout that I outlined here, there's another option. We can use the first, middle, and last labels in the descriptor to deliver only 1 interrupt per batch. So that's another mechanism for interrupt mitigation that might be helpful. And of course, it works for IO mitigation as well. This is possible if the requests are supplied in batches. That is, for example, the case with modern Linux networking, which has a flag per packet that is transmitted that tells you, okay, this is the last one. So we could say, okay, let's set the last flag now. Again, it's not implemented yet, but should help, right? So what else is left to benefit from these performance gains? First, we need to determine whether making descriptor writables like this has any security implications. For example, I seem to remember that the shared memory device did want the invariant that each descriptor is either writable or readable by each side. So, okay, that's worth considering. We need to do testing on more than just Intel processors. All different architectures really behave significantly differently with respect to cache and synchronization. So the code is out there in the Linux kernel, so you can just run the benchmark. And you might need to implement a couple of lines in assembly for memory synchronization if I didn't put all the barriers in there yet, but it should be easy. So really would appreciate help with that. And of course, yeah, if it works well, we will want to implement it, and that's a lot of work to do it on all levels. Okay, let's talk about something different. This is a very interesting recent development, is support for IOMMUs. Traditionally, Virtio completely ignored the virtual IOMMU even if guests attempted to configure it. And this was done for performance, but it prevents applications such as using user space buffers with VFIO on Virtio devices. And in 1.1, there will be an option to fix this and actually obey the IOMMU rules. Latest Linux drivers already learned to handle this option correctly. If you set this option, then older guests that also enable the virtual IOMMU will just break. We kind of cannot unbreak them and be compatible without breaking security. So I guess that's how it is. But luckily, this is off by default. Most guests just don't configure IOMMU by default, so that's kind of okay from that point of view. I'll skip discussion of the implementation of that because there is another talk that discusses this. But besides guest user space drivers, we are also likely to see more uses for virtual IOMMU. In particular, there's going to be talk about the vhost PCI proposal, where one virtual machine can access the memory of another one. And in this setup, it might be a good idea to implement a vhost IOMMU so that you somehow limit the damage that a bug within one virtual machine can cause another one. So that's another interesting application for this feature. Here are some kind of crazy ideas. They're just here not because they're very practical, but more like to spur more innovation in the field of Virtio. So, crazy ideas. First, we have the signal multi-distribution device that allows you to send interrupts to CPUs. How about we extend this to a full-featured Virtio APIC? Would that be useful? Well, maybe, because at least some networking workloads actually spend about 20% of their time doing exits related to APIC programming. So that's one thought. Another is that whenever a virtual CPU goes idle, KVM already started doing a bunch of polling, and it seems to improve performance. So would the polling Virtio idle driver make sense at some level to maybe not even exit and stay within the virtual machine? I am not sure. And here's the last wild idea. Kernel guard technology, it's an interesting software project that implemented a lightweight hypervisor with a bunch of hypercalls that allow guests to control the EPT permissions. And so this is useful, for example, if you want to protect your kernel text memory. So it might be better to write protect it also in the EPT and not just in the guest page tables. And as we are extending the balloon device with guest page hints, right? Maybe this can provide the similar functionality. So these were ideas related to new interfaces between host and the guest that we might want to introduce. But there is a bunch of work that you can do just working on implementation. So first of all, Linux always uses indirect descriptors to pack maximum number of descriptors per ring. And maybe we should go easy there and reduce the indirection levels when the ring is mostly empty. Polling on the host really uses a lot of CPU at the moment. And so maybe we can get some hints from the scheduler and improve performance when the host is busy. I'm not sure how to do this exactly, but it might be a good idea. And we need to improve our error recovery. There are two ways to recover from errors. If the error triggers on the host, we might be able to recover transparently, just restart the backend in some way. If the error triggers on the guest, like a guest bug, then we probably need guest to notice that and do a reset from that side. So let's just mention quickly how would one contribute to Virtio. So if you're just sending patches, there are a bunch of mailing lists. It might be confusing, just copy them all if you're not sure. If you're implementing new interfaces, you want to copy Virtio dev mailing list on Oasis. And if you want to make a spec change, notice the bug in the spec, or want to extend it, you want to send the comment to Virtio comment mailing list. Eventually, one of the members of Virtio will open a tracking issue in our issue tracker, and then we'll resolve it and put a change in the next revision of the spec. So let's leave some space for questions. It's going to be a big release, ton of new features. So join the fun. We're really a big community, lots of active contributors. Just on the spec, we have 9 active contributors. And on the implementation, we have tens of people contributing patches. And that's all. Questions? Okay. Thanks a lot.
Oh, sorry. Question.
Oh, yes. I'm sorry.
I have a question about Virtio 1.1.
Great.
So in the new layout, there's basically a bit which says, is this buffer used, right? If you can go back to the...
Let's find that one.
Yep. Can you go actually...
This one?
Yeah, this one. So what if buffers are completed out of order?
Right. So yes, I tried to draw this here. Maybe I just added drawing things.
So does it mean that in the worst case, you will have to scan the bitmap, basically? Like you wouldn't be able to tell what happened in constant time? Is that true?
No. So what happens, right? You take a look here, right? We have a buffer. We have a bunch of buffers here, right? And the host decided to complete the last one first. So it just takes this descriptor and writes it out first. So when the guest is now looking for new entries to store new stuff in there, it will just look at the start of the ring and say, okay, so here's one first. This is the ID. If I need to do some cleanup, I can do it based on the ID, and now I can proceed to the next ring. So you never scan the whole ring.
Oh, I see. So it copies basically the whole thing to the next slot. It doesn't just clear the bit or set the bit.
Right. So if you do out of order, you have to copy the whole thing.
Mm-hmm. Yep,
if you do in order, you can just flip the bit.
Okay, cool. Yeah. Thank you.
I was curious how you measured 20% APIC exits and which fields that was.
Sorry?
So what was your workload when you were saying 20% of the exits were APICs, and which fields in the APIC were being touched?
I'm sorry, that's just hearsay.
Oh, okay. Hearsay is the best.
Yeah.
Thanks.
So with NFV and HPC becoming more of a reality, there's a high need for more frames per second, higher frames per second. And it looks like the changes made for the 1.1 to have a collected fewer reference in cache should also help fewer references for PCI. Do you think it's feasible to have a Virtio 1.1 device terminated as a hardware device instead of in a software on the cores?
So I'm kind of hopeful, yes, because for some reason, like many people discussed doing hardware implementations of Virtio, it never surfaced, and I kind of suspect that our layout is just too complex and expensive to implement. So maybe we do a simpler one, and it will happen.
But are there any hardware contributors giving opinions on the spec, or you don't know?
So yeah, but, I mean, we have on the TC we have people who do hardware, but no one spoke to me about doing this, so I don't know.
Okay, thank you.
I was curious if the APIC exits were from the message passing benchmarks that I published last year, in which case it was the APIC timer register that took a lot of the CPU time. Is that where the hearsay was from?
Oh, how do I measure these numbers? Is that the question?
Yeah.
Oh, so you can, it's a benchmark that I put on Linux kernel. You can find it under tools/virtuos/ringbench. It's not actually running within the VM. It's just two threads that communicate using Virtio. There's an attempt to emulate exits by just doing lots of useless stuff.
Okay, thanks. And the other thing was about having a vhost idle for polling in the guest. I think you don't win a lot by moving the polling from KVM into the guest. You save about 1 microsecond. So depending on what your latency goals are, that's about how much you're going to save. I think ideally, actually, we don't push halt polling up into the guest. We push it down into the scheduler and actually take it out of KVM entirely. But depends on what your goals are.
Yep, that's a concern on some level. I agree. Okay, thank you. Thanks for attention.